Hey, welcome to the Explainer. Today, we're going to do something pretty cool. We're starting with just one single simple thing, an electric charge. And from there, we're going to build up to one of the most important structures in, well, the entire universe, the electric dipole. And really, this question is everything. See, going from one charge to two, it's like going from a single musical note to a full-blown chord. You get this totally new system, a whole new kind of behavior. And that's what physicists have a name for, the electric dipole. All right, so here's the game plan. First, we'll nail down the field from a single charge. Then we'll build our dipole, check out its field from a couple of different angles, see how they stack up, and for the grand finale, we'll see what happens when we make it spin. Okay, first things first. Before we can even think about a system with two charges, we gotta master our basic building block, right? And that's the electric field from just one single charge. So, what is an electric field? The best way to think about it is like an invisible force map that fills up all the space around a charge. It's basically a cheat sheet that tells you exactly how much of a push or pull another charge, what we call a test charge, would feel if you dropped it anywhere on that map. All right, so how do we get to this formula? Well, it's actually pretty clever. We start with the basic force equation between two charges, and then we just divide out our little test charge. And here's the really beautiful part. The test charge just cancels out completely. Gone. Which proves something huge. The field is a property of the source charge, Q, and how far away you are, R. That's it. Nothing else matters. Okay, so we've got our building block down. Now let's do what we came here to do. Let's stick two of them together and see what happens. And trust me, what we create is something you find everywhere in nature. And here it is, the electric dipole. Seriously, just look at it. It's basically a tiny barbell that's electrically neutral overall, with a positive charge on one end and an equal negative charge on the other. And this simple little setup, oh, it's everywhere. We're talking about the water molecules inside you right now, all the way to the antennas that are sending out radio waves. Now, instead of talking about two separate charges all the time, we can be much smarter about it. We can describe the whole system with just one single thing. A vector we call the electric dipole moment, or P. It's so convenient. It just packages up the strength of the charges and how far apart they are into one neat little number that tells you everything you need to know about the dipole's personality. Okay, now for the fun stuff. Let's actually calculate the electric field that this dipole makes. We're going to start by looking at a point that's directly in line with it, sort of a head-on view, right along the axis that connects the two charges. The approach here is actually pretty straightforward. We just put a point on that line and figure out the field from each charge one by one. The positive charge is going to create a field that pushes away, right? And the negative one is going to create a field that pulls in. Since they're basically having a tug of war along the same line, all we have to do is see which one is stronger at that point and add them up. Okay, but let's be real. In most situations, you're not going to be right up close to a dipole. You're going to be looking at it from pretty far away. So when our distance r is way, way bigger than the tiny separation a between the charges, we can use a really handy shortcut. It's an approximation that makes the math a whole lot easier. And check out what we get. This super simple formula tells us something incredibly important. The field from a dipole, it drops off as 1 over r cubed. Now hang on. Remember a single charge? That was 1 over r squared. This means a dipole's influence just fades away so much faster as you get further away. And it makes sense, right? From a distance, that positive and negative charge start to kind of cancel each other out. All right, let's switch things up. What happens if we look at the dipole not from the end, but from the side? Let's figure out the field at a point that's right in the middle on that line that cuts it perfectly in half, what's called the equatorial line. Now this time, things get a little trickier. The fields from the positive and negative charges aren't lined up anymore. Nope, they're both pointing at an angle. And that means we can't just add the numbers together. We've got to break out the big guns, vector components. But here's where the beautiful symmetry of the whole setup really helps us out. Just picture it. The positive charge pushes up and to the side, the negative one pulls down and to the side. But because our point is perfectly in the middle, that up part and that down part are exactly equal and opposite. So poof, they cancel each other out completely. All we're left with are the parts pointing sideways, and since they're both going in the same direction, they just add right up. So after we run the numbers and use that same short dipole approximation, we end up with this another beautifully simple formula. And if you're thinking, hey, that looks kind of familiar, you're absolutely right.
It's really similar to what we got on the axial line.
Okay, so we've got our two big results. Let's throw them up side by side. Because when you see them together, you realize there's this incredibly simple, elegant relationship between them.
Just look at that. At the same distance r away from the dipole's center, the formulas are practically identical. You've got the dipole moment p, you've got the distance r cubed. There is just one little thing that's different.
Yep, that's it. It's just a factor of 2. The electric field along the axis is exactly twice as strong as the field at the same distance out to the side. How cool is that? A perfectly clean, simple, powerful ratio. Okay, so up till now, we've been all about the field that a dipole makes. But let's flip the script. What happens if we take our little dipole and drop it into someone else's electric field? Well, something interesting happens. It doesn't get pushed, it gets twisted. And this twisting action has a name. It's called torque. The external field puts a little force on each of the dipole's charges, and those two forces work together to make the whole thing want to rotate, to try and line itself up with the field. So here's the play-by-play. The field pushes the positive charge in one direction, and it pulls the negative charge in the exact opposite direction. So the net force is 0. The dipole as a whole isn't going anywhere. But, and this is the key, because those forces are happening at opposite ends, they create this turning couple. It's exactly like pushing on opposite sides of a steering wheel. The wheel doesn't fly across the car, it just spins. And this formula really tells the whole story. The amount of twist or torque you get depends on 3 things: the dipole's own strength P, the strength of the external field E, and, crucially, the angle between them. You get the maximum possible twist when the dipole is completely sideways to the field, at 90 degrees. And the moment it lines up perfectly, the torque drops to 0. No more twist. And get this, that spinning action on water molecules, which are just little natural dipoles, that's literally how your microwave heats up your food. The field makes them twist back and forth like crazy, and that's what generates the heat. It's amazing, right? From how molecules hold together to how antennas send out signals, this simple little pair of charges is behind so much, from the tiniest scales all the way up to the world we interact with every single day.